For section 4.2, we're looking at translations of the graphs of sine and cosine functions. Okay, so that sort of changes our formulas, the way we're going to look at them. And here's the way your book lists these. Instead of just y equals a sine bx and a cosine bx, we now have a c and a d coefficient or constant kind of added in there. So our new formulas are y equals c plus a sine b parentheses x minus d, or y equals c plus a cosine b parentheses x minus d. So you're going to have to do a little adjusting and kind of, it'll take a little while, but once you figure out what each of those numbers mean, a, b, c, d, these are not bad at all. First, what you have to do is you have to factor b out of the parenthesis if necessary. So if there's something in front of the x inside the parentheses, you just force factor it out. We'll look at that. The little d is called the phase shift in a trig function. In an algebraic function, it's called the horizontal shift. The one in parentheses is your horizontal shift. So the one in the parentheses is your phase shift. Remember that these act in the opposite direction than you would normally think. That's how horizontal shifts do. If it says minus 3, it would actually go 3 to the right. And if it says plus 3, it would go 3 to the left, because your phase shift would actually be negative 3. So it's your opposites. You have to be really careful with that. Little c is the vertical shift. If there's a positive 5 in front, it will go up 5. If there's a negative 5 in front, it will go down 5. Vertical shifts act the same way you always expect them to. To graph these, what we're going to do is we're going to first ignore c and d. And we're just going to graph y equals a sine bx or y equals a cosine bx, just like we did in section 4.1. We're just going to make a table for those. Then we will adjust that table and the graph accordingly, depending on what c and d are, what your vertical shift and what your phase shift are. So we'll just move every point left or right by d and up or down by c. It's really easy. It's not a bad section. And if you missed the previous section, it reviews that as well. Just a quick note, your book will sometimes refer to the argument of a trig function. The argument of the trig function is that parenthesis x minus d. So if a trig function has a phase shift, that parenthesis is referred to as the argument of the trig function. I don't use the terminology a lot, but if you ever see it, that's what it means. So we'll pause right here for a second and let you take a few notes. For this problem, we want to graph y equals sine of x minus pi over 3. And we're just going to draw the graph over one period. To me, the best thing to do is to go ahead and identify little a, little b, little c, little d, and decide what each of those tells you. So we're going to take little a. Which one of those numbers is little a?
It's understood.
It's understood to be the coefficient of the trig function. Yeah, so what's in front of the sign here is an understood 1. Little b is what's in front of your x. So what's in front of the x? 1. A 1. Little c is what is added or subtracted in the very front. 0. So c in this case is 0. And little d is what is subtracted on the inside. So little d is the opposite of what you think. It is positive pi over 3. Okay? And now we're going to talk about what each one of those tells us. What does little a tell us? It tells us the amplitude of a sine and cosine graph. So this tells us that our amplitude is the absolute value of 1, which is 1. Little b helps us find our period, which is how long it takes on the x-axis for the y values to start repeating. The period is 2 pi over b, which is just 2 pi. Little c tells us our vertical shift, which in this case is nothing, so it's not going to move up or down at all. And little d tells us our phase shift, or our horizontal shift. In trig, that's called a phase shift. So positive pi over 3, is that going to move it to the right or to the left? Left. To the right, yeah. Remember, it's the opposite of what it looks. It looks like a negative pi over 3, but it's actually a positive pi over 3, and that's going to move it to the right. So that's to the right pi over 3. Do we have any questions about little a, little b, little c, little d? Okay, once you know those 4 things and you've determined what they mean, ignore all of that for just a little bit and come down and just make a table for y equals a sine bx. So you ignore c and d. So we're going to look at the table for just y equals a sine bx, which is just 1 sine 1x. And that's what we're going to build our table for. Okay? So we start at 0, skip 3 spaces, and our final slot is always our period. So 0, skip, 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 2 pi. All right? Sine of 0 is 0 from your unit circle, and we know that the sine graphs always go through the origin before they've been shifted. They may not still be at the origin once you shift, but before you shift it, they should go through the origin. Let's fill in these. I forgot about that. Let's do pi, pi over 2, and 3 pi over 2. So this is 0. What should this be? It should be the value of a, right? So let's see if it is. The sine of pi over 2 is positive 1, and then it should alternate 0, and then the opposite of a, and then back to 0. So that's pretty easy to build that table. Now that is not what you actually graph. Now some people prefer to go ahead and graph that and then just move all the points over. What I actually prefer to do is just to make a new table. Okay, so that's how I'm going to teach it. It's a little different than how your book teaches it. I don't care if you know, what they'll do is some people will move that and then shift everything to the right, pi over 3. Here's the problem. Where is pi over 3? You know, if you're at pi over 2, where's pi over 3? So it gets to be a little complicated there. So I think it does better if we go ahead and shift it. Okay, so now we're going to make a shifted table. We're going to make a table for y equals sine of x minus pi over 3. So we're going to remake our table. We'll talk about these x's and y's. Now listen very carefully here. What is being changed? Am I changing the y values or am I changing the x values here?
X's.
The x's. I'm changing the phase shift to the right. So I'm actually going to move all of those to the right pi over 3. So instead of plain x in this table, I'm going to put x plus pi over 3. Am I changing my y values at all? Do I have a vertical change? No. So those will stay. So those are easy. But when you shift, you have to, move your phase shift. So we're going to add pi over 3 to each of our x's to shift it to the right. So let's build that table. 0, 1, 2, 3. I can't count. 1, 2, 3, 4, 5. Okay. Now I need to add pi over 3 to each of those x's. So if you imagine adding pi over 3 just to the x's, what's 0 plus pi over 3?
Pi over 3.
Pi over 3. What is pi over 2 plus pi over 3?
Pi over 5.
Let's see. That's pi over 2 plus pi over 3. We get a common denominator. Or if you want to, you just take 1/2 plus 1/3, right? So a common denominator, that would convert, I need to multiply top and bottom by 3, so that's 3 pi. And that needs to be multiplied by a, so that becomes 3 pi plus 2 pi over 6. So 5 pi over 6. Now I don't care how you get there, but at this point you have to be able to add some fractions together. So if you ignore the pi's and you add 1/2 plus 1/3, you get 5/6. All right, now if I take pi and I add pi over 3,
4 pi over 3.
that's 1 plus 1/3, which is 1 1/3. So in other words, it's 3 pi over 3 plus 1 pi over 3, which is indeed 4 pi over 3. And then I take 3 pi over 2 and I add pi over 3 to it. 3 pi over 2. Help. Get a common denominator of 6. Multiply this one by 3, right? Which is what?
11 pi over 3.
Just this one. This one's going to be 9 pi over 6. And that one would be 2 pi over 6 for a total of 11 pi over 6. And finally, if I take 2 pi and add pi over 3, Still a common denominator of, this time it's 3, right?
Oh,
Yeah, this time it's 3. So that's going to be 6 pi plus 1 pi gives me 7 pi over 3. So you can see that these are very, very, very ugly.
Oh,
Hang on, I'm going to pause right here and let everybody think about their table for a minute. But let me fill in the y's. They don't change. This stays 0, this stays 1, this stays 0, this stays -1, this stays 0. So we only adjusted our x's because we only had a phase or horizontal shift. Let's pause for a second. Okay, so now that everyone understands the adjusted table, what we're going to do is we're going to take this and we're going to graph just the red portion. Now your book graphs them both. Your book graphs the first one and then shows what it does is it takes each of those points and it slides it to the right pi over 3. I've found that it's easier just to graph one so it doesn't get all crazy, but you can show both, you know. So we're going to start here. And how far out do I have to go to get to this? I have to get to 7 pi over 3, right? Well, here's the thing. I have found that it's best to use your common denominator to count. Okay? So what is my common denominator? 6. So if I'm going to count by 6, this is going to be 1 pi over 6, 2 pi over 6, which really reduces to what? 1/3. 3 pi over 6, 4 pi over 6, 5 pi over 6, and 7 pi over 6. Uh-oh. I'm nowhere near, y'all, this isn't going to be big enough. 7 pi over 6. How far do I need to go? What would this one be over 6? I need to get to 14 and I don't have enough room up here, which I did not anticipate. It needs to actually be twice as long as this. What should I do?
Count by.
I should pause and redraw it?
Yes.
Oh, okay. Okay, so here's what we've done. We've erased part of this so that we can still see it all up on the board. And I have graphed all the way out to 14 pi over 6 because that is the equivalent of 7 pi over 3. So I got a common denominator and I showed a slot for each one of those. And I used the increment of pi over 6 so that I could see everything that I needed. So you have to make sure your graph goes out to your last point. That's how I knew it needed to go out to 14 pi over 6 and I was in trouble over here. So now that we have that, we're just going to put these red dots on. At pi over 3, I'm going to put 0. So where is pi over 3? 2 pi over 6, okay? And then at 5 pi over 6, I'm going to go to 1. And then at 4 pi over 3, I'm back to 0. So we have to figure out what that one is. That's 8 pi over 6, right? Now some people like to come off to the side of their table and like show that. Like if it's not already over 3, they'll go ahead and convert it. So they'll say this is 2 pi over 6. That one's already over 6. This one would be 8 pi over 6. This one's already over 6, and that is 14 pi over 6. So this is where knowing fractions really comes in handy. All right, we have our first 2 points. Now we want to put our third point. Our third point should be at 4 pi over 3, which is the same as 8 pi over 6. So it shows up right here. Then at 11 pi over 6, we're down to -1. And at 14 pi over 6, we're back to what? 0, yeah. Okay. So it looks like this. So it's a little hard to see, but all sine and cosine graphs kind of look the same, right? Just sometimes they're more spread out than others. And I really took a lot of space to show you this. So some of you could fit that in a smaller space. And you don't have to show a number at every dot. I just wanted, like at every increment, I wanted to make sure you understood where I was getting those numbers from. And other instructors care, but I don't. Like sometimes they like you to go ahead and reduce these as you go. Like reduce this to 1/2, reduce this to 2/3, reduce this to 1. It doesn't bother me. They're equivalent, so you can leave them, but it's up to you. If it bothers you, you can reduce them. So that is the very first problem. It's going to be a long lesson, isn't it?
Not really. There's only 8 slides.
Let's break right there.